Okay, let's start. Today I'm going to talk about haha, now it's working. Parametric estimation for a system of interacting particles, which is based on a joint work with my supervisor Mark Podolsky, Vitote, and Akram is here too. What are we going to do today? Okay, first of all, we want to introduce the model. We want to understand what we want to do. Okay. What has already been done? Let's see a bit of the previous literature, and then we'll be ready to start with the real talk, with the assumptions. We'll see some examples that satisfy our assumption, and we can actually provide our main result, we can arrive to the conclusion, and we can talk about some open questions as well, which is always a nice way to finish a talk, I would say. So let's start. What are we going to consider? An interacting particle system. What does it mean? Well, you can see here that we have several stochastic differential equations, okay, depending on I. So we have capital N stochastic differential equation. Each one is a particle. And here you can see that in the drift and in the diffusion coefficients, there are two parameters, θ1 and θ1, which are the object that we want to estimate. Then what? Well, the point is that there is some interaction among the particles. And this is modelized by the fact that in each equation, the coefficients depend on the parameter that we want to estimate, depend on the particle itself, and also depend on this mu Tn, which is the empirical measure as said here. Another thing which is important to say is the fact that we start from some Brownian motion and Brownian motion, which are independent among them, but then the particles are not. Why that? Because of this empirical measure I was talking about before. And we'll see that that's the main reason why considering this model it's way more challenging than considering some classical stochastic differential equation. So the point here is also that I would like to give some intuition about what's challenging, and I would like to compare our results to the results in the classical SD case, which are known in the literature. Also, we have to understand how to work with this measure, and so I have to give a bit of notation. In particular, I have to introduce this Wasserstein two metric we are going to work on to give the distance between the two measures. And here, again, what's important to say is that we have these coefficients, B and A, the drift and the diffusion coefficients, which are really general. We are going to see that this is basically the main novelty compared to the previous literature, which is the fact that both the coefficients depend on some parameters we want to estimate, depend on the process, and depend on the empirical measure too. Okay. Then, why do we want to do that? Well, it's interesting to see that there aren't a lot of papers about stochastic, about the interacting particle system, which aren't recent. Why that? Well, because apart from one paper, which is Kasonga paper, we'll see later together, the problem was that at the beginning, this system were introduced by McKean in 1966 to model the dynamic of plasma. And what's the problem there? Well, there were no data, okay? It had a lot of application in statistical physics, but over there, it was impossible to see the data, to have them, and so there was no reason to do any statistics about it. Then everything changed when we actually understood that this was a good model to consider also some other applications in other subjects. And in that topic, we actually have a lot of data. So now it makes sense to do statistics, you see, because now we have the data. And which are the applications? Well, we have a lot of them, to be honest. We are going to see better some of them with some application, with some examples. But the idea is that, for example, we can see how some animals interact. So there are a lot of application in mathematical biology, the fact that the behavior of an animal interact with another animal. Then we have a lot of application in social science, for example, opinion dynamics in finance. This is a very good model to understand the bankruptcy and how the banks are connected one to each other. The fact that if you get bankruptcy on one side, then it's likely that someone else will have bankruptcy as well. And it's a good way to model those cases in which we have a large number of players, okay? This was a very general introduction, but now we want to move forward and we want to consider our special case. So what about statistics? What do we know already? Well, we can start with some papers. And as you can see here, well, it's exactly what I said before. There is Kazonga paper, which is from 1990, and all the other are really, really recent. In Kazonga paper, what does he do? Well, he considers an interacting particle system, and he assumed that his model is easier because he has linear dependence on the drift coefficient, then the volatility, the diffusion coefficient is just a constant. He assumed that he has continuous observation of the process, and then he just wants to estimate the drift. How? Using the maximal likelihood estimator. It's the most natural way of doing that. Well, for us, things are going to be different. Why that? Well, because we do not dispose of the continuous trajectory of the process, but we just consider some discrete observation. Another thing which is interesting is the fact that for us, the time horizon is fixed. Why is that interesting? Well, because if we consider classical stochastic differential equation, I don't know if I'm expert about it, but if you're familiar with this case, what happens is that if the time horizon is fixed, there's no way you can estimate both parameters, okay? Why can we? Well, because our asymptotics is for capital N, which is the number of particles, going to infinity. So here we can see already that the role played for classical SDE by the time horizon is now played by the number of particles. And in this particular context, there are some other interesting papers. There are actually, well, it's not a hot topic right now, so there are a lot of asymptotic regimes that have been considered, for example, by Valentina, Caterina. Well, they consider also what happens for small noise, or, well, there's an important paper by Vitote, Mark, and Denis, where they consider the semi-parametric estimation of the drift. It is really to say that it's a living topic, and as you can see, all these papers are really recent. So there's a lot to do. And now we're ready to explain a bit better what do we want to do in detail, and which are the main novelties compared with what we had before. Well, as seen in the very first slide, our coefficients are really general, okay? We have drift coefficient and diffusion coefficient that can both depend on the law itself. And we want to estimate jointly the two parameters in the drift and in the diffusion. And we'll see that it brings to some difficulties. Not surprised, we are not surprised about it because it was the case also for classical SD. If you want to estimate both parameters, of course, things are more complicated. And why is that important? Well, because there are a lot of applications, especially in finance, to the case where the diffusion coefficient is general, especially when you want to calibrate the parameter in a model in case where the market is with the smile. So we start from our discrete observation of the interactive particle system until a time t, which is fixed, and we want to estimate θ1 and θ2. How? Well, the classical idea, the natural idea, would be just to consider the maximal likelihood estimator, right? But we have discrete observation, so transition density is not available, maximal likelihood is not available, but the idea is to introduce a contrast function which plays the same role as the maximal likelihood estimator, where we approximate the diffusion using an Euler scheme. We get this contrast function, and then we propose the estimator by looking for the minimum of this contrast function. And here already we can try to consider what happens in the classical SDE case and do some kind of comparison. And the main difference is that we have this extra sum over the number of particles, which so far doesn't seem to be a problem, but we'll see that it is. Now, we have to add some assumptions on the coefficients. And of course, it's just after lunch. I don't want to enter in detail. I don't want you to get asleep. So it will be very, very fast, I swear. The only one thing that I really want you to remark, it's not this. It's not this. Let's stay here. The only one thing that I want you to remark is, first of all, that we really need the Lipschitzianity of the coefficient, which is a natural request. But as the coefficient depends on the measure 2, well, the Lipschitzianity is with respect to both. There, I haven't said anything yet. The other thing that I want you to remark is that sometimes we have two different types of assumption. For example, in A4. Why that? Well, because the first one is enough to get the asymptotic the consistency of the estimator, while if we want also the asymptotic normality, we need to ask something more. And this is going to be the leitmotif of this talk, because we'll see that to get the asymptotic normality, things will get more complicated. Okay, and in particular, we have to consider some other assumptions as well. And here, again, A5 and 6, don't even look to them. They are really natural. But at A7, it's the assumption that bothers me. Why that? Well, because I spent the first 15 minutes talking about the fact that the model is super general and wow, we are super happy about it. And then, bam, I'm putting an assumption on the diffusion coefficient. Not so cool. True. But there are some stuff that we can say about it. First of all, we need this assumption only for the asymptotic normality. Second of all, this is needed to get the asymptotic normality of the diffusion coefficient. But if you want, and we'll see later why, but if you want to estimate only the drift coefficient, we don't care about the fact that in the diffusion, there is the dependence on the law too. This is not going to be a problem. And this is already a big extension compared to the previous literature, okay? But if you want to estimate the diffusion coefficient, we'll see later that the point is that we have to derive with respect to the measure, and we had to add this assumption in order to do that. So we have some assumption, and in order to be cool, show some application that actually satisfy all assumption in real life. First model, the Kuramato model, is used to model the synchronization. So it is, for example, when you want to consider the behavior of some societies of animals, okay? But also for the clapping crowd. And the fact that if there is someone starting clapping, then you heard it, and then you start clapping as well, and so on. And at the end, everyone will clap at me. So that's the point. That's the first one. The second one is even a hotter topic, I would say, because the point is that the system of interacting particle has been used to model opinion dynamics. And in particular, an epsilon variation of this model has been used, connected to COVID, to understand how people was reacting to vaccine. I mean, not really to the vaccine, but the opinion of the vaccine. And after that, there are some other applications. I'm going to go faster. So here, for the third one, we have a lot of application in finance. And I was saying before, it models basically the behavior of the banks. Like the fourth one is the Ornstein-Uhlenbeck process, and I don't have to explain to you the importance of this one. So now, everything is ready. What did we do? Well, we have proposed an estimator And we have said, yeah, the estimator is a good one. Why that? Well, because it was possible to prove the consistency of our estimator and the asymptotic normality up to add this assumption on the rate at which capital N, the number of particles, is going to infinity, compared to the discretization step. Okay, and we're going to talk better about this assumption later. Now I want to give you just an idea of why things get challenging in our context. How that I give you the idea of the proof for the asymptotic normality. And the idea is to say, okay, well, using mean value theorem, we can write directly this using the fact that our estimator, well, satisfies the minimum, so the derivative is 0, so we can write this extension. And now it means that if we want to get the behavior of this estimator, well, it's enough to study the behavior of the derivative of the contrast function and the second derivative. In particular, we're going to show that the first derivative here converges in law of Gaussian, and this guy is going to converge in probability uniformly to some matrix we'll see later. So really the first step is to show this convergence in law. This convergence in law is going to be based on some central limit theorem or marginal difference array. And here the point is that, well, we consider this sum over the observation of this quantity called Z. And the point is that inside the definition of Z, there is the sum over all the particles, which is going to be a problem. Why that? Well, problem. This is going to be challenging. We solved it, otherwise I wouldn't be here talking to you about it. But the point was that in order to show this central limit theorem, we had to consider not only Z, but its moments as well. And if you want to consider the moments of something in which there is this sum over capital N, well, there is a problem, because then you have like n to the power 2 and so on, or n to the power 4 in the last condition, and this n is going to infinity, so it's big. If you want to show that it converges, as in the second case, to something which is finite, good luck with that. How can we do that? Well, the idea is to say, it's true, it's a problem. Like it is, it's a problem. But we have to remember that we started from some particles which were not independent, because, okay, there was the interaction, but the Brownian motion were independent. So this is still not enough, but maybe there's something we can do about it, right? Yes, that's exactly the idea. Here, the important thing to remark is that we study some conditional expectation of this quantity Z, okay? And the conditional expectation is with respect to, okay, some J-1, it means that we arrive in particular to that observation. So here the main point is to say the Brownian motion are independent, but we have a problem because, however, we have xs and μs. But, however, we can recover something which is measurable with respect to the sigma algebra we are considering. And then the randomness basically is going to be given by this Brownian motion which were independent. The problem is basically solved. So we have to be able to move to this random variable which are measurable. How can we do that? Well, the Lipschitzianity is going to help us a lot, but sometimes it's not enough. One particular case that is not enough because we need to use the fact that the stochastic integral is centered. And if you bring inside the absolute value, well, this is not going to happen. So there you really need to use Ito formula. And to use that, well, you have to derive the diffusion coefficient with respect to the process and with respect to the measure. And that's why we really needed assumption A7. That's how we have introduced that. However, we were able to arrive till the end. Of course, I'm not going to explain in detail also the other steps. That was just to give you an overview, one of the main challenge in our context. We were able to arrive till the end, and so after having proven also these convergences, everything was done, because we were able to get exactly what I was talking about before, which is the convergence in law of the first derivative, convergence in probability of the second derivative. It's uniform. Bam, you use Lasky and you get the convergence law that you wanted, so you actually get the asymptotic normality. We can put stuff together saying, okay, we have proven the consistency of the estimator. Cool. And the asymptotic normality, but up to add this assumption. On the convergence rate of the discretization step, basically, we are saying that it has to go to infinity fast enough. And at the beginning, we weren't so happy about it because, I mean, it's still an assumption that you have to add. So, first question we asked ourselves was, is there an analogous condition for the classical SD case? The answer is yes. I mean, we have said before that the role played by the time horizon is now played by the number of particles. And as you can see, when Flores-Mirou introduced the problem for classical SD, she actually found basically the same kind of condition. The point was that that condition was then improved by Nakahiro, 1992. And the problem was completely solved then by Kessler in 1997, introducing a contrast function which was more complicated on one side because it wasn't explicit. So it was depending on some quantities which weren't explicit, but it was constructed on purpose in order to not to have any condition. Here we are saying that the discretization step can go to 0 at a polynomial rate, no matter which one, in order to get the result. And then the very same thing has been done in the case of stochastic differential equation with jumps. So a question could be, well, is it possible to improve the condition for you too? Maybe. Don't have enough time to actually discuss it in detail. So far, maybe it's enough. There are some other interesting questions. If you're interested, we can discuss them later, of course. Another question is, okay, you have proven that the estimator is consistent, it's asymptotic normal, and the variance is known. So one could ask, okay, but is it efficient or is it possible to do something better? Let's say it's efficient, but maybe I'm saying too much. Why that? Because in a very recent paper from Mark Hoffman and Letizia Della Maestra, it has been proven the LAN property for the drift estimation. And they found a Fisher information which is exactly what we find in our framework for the estimation of the drift. So we can say that for the estimation of the drift, what we have done is actually asymptotically efficient. What about the estimation of the diffusion coefficient? No but. But if we consider the classical SD case, Manuel Gobet showed that the LAM property holds true, and he found the Fisher information, which is, again, with a bit of fantasy, with a bit of imagination, basically the same as in our case. Why a bit of imagination? Well, because for him, of course, it was the time horizon going to infinity, so he had an invariant measure, and so, of course, the integral he was considering was a bit different. But if we follow the comparison that we have done before, and we keep saying that the role played by capital T is now played by capital N, then actually what we found it is the same. Okay. But still, that is one of the open questions that now I propose to you, actually, about the efficiency of the diffusion coefficient as well, which is something Akram is working on now. Then, how to improve the condition. What I had time to say is that it's a bit more complicated. It's more complicated than the classical SDE case, because there are the same problem they had, plus 1,000 others, say. And then there are some other interesting things, just because, as I was saying before, this is a hot topic, this is super new, so there are plenty of stuff we could do about it. It's just that we should have enough time to do all of them, okay? But for example, it's interesting to understand what happens if we have the jumps as well, or what happens if we want to consider a process which is multidimensional. And another thing is about the semi-parametric estimation, again, or non-parametric estimation of the drift. This is one of the open problem if we want to recover some polynomial rate, and it's something else we are working on, again, Mark and Shiwi. And that's it. This is the paper the talk is based on. By showing you the references, I conclude. And I thank you again for everything. That's it.